So is my slide visible to all of you?
Yes, sir.
And am I audible?
Yes, sir.
Yes, sir.
Okay, okay. So let us start the discussion. So we are here for week 5 discussion for this course, deep learning, and this course was originally taken by Professor Sudarshan Iyengar, Professor and Head of the Department of Computer Science and Engineering, IIT Ropar, and myself, Ayan Paul. I am a PMRF research scholar from IIT Kharagpur. I am a PMRF TA for this course. My duties are to solve some of the question related to your assignment, so that whenever you will be solving the assignment, you will not feel something new. Okay, so that are my duties. But what I prefer is to discuss some of the theories related to this week, so that when you are solving the question again, it will be easier to all of you. Okay, so that is the thing. Yeah. So last week, what we have discussed regarding this gradient descent and this momentum based gradient descent, Nesterov accelerated gradient descent. Then we have talked about that, we have discussed about that stochastic gradient descent, mini batch gradient descent, and lastly we have discussed about the three algorithm, that is this ADAGRAD, Adam, and RMS prop. Okay, today we will be discussing something about PCA, okay, principal component analysis. So before that, PCA is related to eigenvectors and eigenvalues. Okay, so it is important to know what are these eigenvectors and eigenvalues. Okay, so uh, you can see this. Okay, so this is the matrix, A matrix, and this is a vector x. Okay, x equals to 1 1 3. Okay, so this is a 2 cross 2 matrix, and this is a 2 cross 1 2 cross 1 vector. Okay, so what happens if A is multiplied by x? Whenever a matrix is multiplied to a vector, the vector changes both its direction and magnitude. Okay, you can say this is the direction of the original vector. Now the direction has changed to this way, and also earlier this was the magnitude of the vector. Now the magnitude has also increased. Okay, so this is the characteristics of matrix. Whenever a matrix is multiplied to a vector, it always changes its direction as well as magnitude. But the thing is, what we are interested in finding some vectors. Whenever that will be multiplied by a matrix, it will not change its direction. The magnitude will be altered, but it will not change its direction. So what type of vector these are called? These spatial vectors are known as eigenvectors. Okay, so here you can see, earlier whenever we are multiplying a matrix to a vector x, what happens is the matrix we are changing the direction, and the direction as well as magnitude of the vector changes. But here the magnitude is only changing, but direction remains the same. So this type of vector are known as eigenvectors. Okay, so this is the thing. And eigenvectors, we can write the eigenvectors by this. If A is a matrix, the vector associated to that matrix, which will not change its direction if it is multiplied by that is the eigenvector, that is x vector. Okay, so A x equals to lambda x. What is this lambda? This lambda is known as eigenvalue. So I have told you, what will happen is the vector will not change its direction. So x remains the same, but its magnitude is changing. So that is why lambda x. Okay, so lambda is the eigenvalue and x vector is the eigenvector. Okay, so this eigenvector and eigenvalue are the characteristics of a matrix. So the characteristics of this matrix A has a eigenvector, that is x, that is 1 comma 1, and it will have an eigenvalue, that is lambda, and this lambda will be equal to 3. So this is the theory related to eigen. Okay, someone is joining. Okay, so this is the theory related to eigen vectors and eigenvalues. Now, to have a formal definition, eigenvectors are the direction that remain unchanged during a transformation, even if they get longer or shorter. That is, the magnitude can change, but its direction will not change whenever a matrix is multiplied to that vector. So this type of vector are known as eigenvector. And what are the eigenvalues? Eigenvalues are the number that indicate how much something stretches or shrinks during the transformation. Okay, so how much the magnitude is changing during the transformation, that is known as eigenvalues. So the word eigen, where does this word eigen has come from? It is a it has a German origin, which means characteristics. Okay, eigen means characteristics. Why eigen means characteristics? Because eigen vector are that characteristics vector are that vector whose characteristics will not change. That is, its direction will remain same. Okay, whenever it will be multiplied via matrix. So this is regarding eigenvector and eigenvalues. Now the question is how to find this eigenvalues and eigenvector. So we have a matrix A. For example, we have a matrix A. Then how we can find this eigenvector and eigenvalues? So see, this equation we just have discussed, that is Ax equals to lambda x. So just taking lambda x on the left hand side and taking x common, we have arrived this equation. Okay, now x cannot be 0. Okay, x is a vector, so it cannot be 0. So a minus lambda I mod will be 0. So whenever we will be doing this a minus lambda I, a minus lambda is also a matrix. So whenever we will be doing this a minus lambda I, so it will give an equation. That equation is known as characteristic equation of the matrix. So by solving this equation, what we will do is we will be finding the lambdas or the eigenvalues. Once we get the lambda, we will put in this equation and we will find the x. That is the eigenvector associated with this eigenvalues. So this is about eigenvectors and eigenvalues. So some definition and theorems related to this concept. So if this lambda 1, lambda 2, lambda n be the eigenvectors of n cross n matrix, then lambda 1 is called dominant eigenvalue of A if lambda 1 is greater than all other eigenvalues. That means you will be, whenever you will be solving this equation, you will get a different set of like if you have 2 cross 2 vector, then you will get two values of lambda, that is lambda 1 and lambda 2. If the lambda which is greater than all other lambda, like lambda 1 is greater than all other lambda, if there are 2 lambda, then lambda 1 is greater than lambda 2, then lambda 1 is known as dominant eigenvalue. Okay, and what is the second definition? A matrix M is called a stochastic matrix if all the entries are positive and sum of the elements in each column is equal to 1. That means any matrix like this P 1 minus P and this 1 minus QQ, if P is such that it will never do all the elements, it will never transform the elements to a negative value, then this matrix is known as stochastic matrix. Why it is called stochastic matrix? Because each column, if we sum each column, that is P plus 1 minus P, that will give 1. Okay, similarly 1 minus Q plus Q, that will be give 1. So this type of matrix is known as stochastic matrix. So we have two theorems related to this. First, the largest dominant okay, someone is joining. Okay, so two theorems that are associated with this. First, the largest dominant value of a stochastic matrix is 1. So whenever we are talking about this type of matrix, the largest dominant eigenvalue or the dominant eigenvalue of that stochastic matrix will be equal to 1. And second thing, if A is an n cross n square matrix with dominant eigenvalue, then this we don't need to discuss here. So these are the things. So is it clear what are eigenvalues and eigenvector? Is it clear? Clear, right?
Yes, sir.
Okay. So everyone understood how we can find eigenvalue and eigenvector? If I give you a matrix, can you find the eigenvalue and eigenvector? Can you do that? Okay, no response to this. Okay, you can do that. Okay, so let's practice a question related to this. Okay, how to find the eigenvalue and eigenvector. So this is our matrix, A matrix, that is this has elements 1, 2 and 5, 4. Okay, now we have to find the eigenvalue and eigenvector. So what is the first step? First step is we have to find the characteristics equation. What is the characteristics equation? This magnitude of A minus lambda I equal to 0 will give you a characteristics equation. So we will be finding the characteristic equation first. So that is mod of A minus lambda I, or determinant of matrix means we have to do to find the magnitude, we have to do the determinant. So we have to find the mod of this A minus lambda I. So whenever we will do this A minus lambda I, we will be arriving this equation. Okay, whenever we will be equating this equation to 0, so this equation is known as the characteristic equation of this matrix. So by this equation we can find out the eigenvalues. So just we will factorize it, and we have this two eigenvalues, that is 6 and minus 1. Okay, now we got this eigenvalue. Our second task is to calculate the eigenvectors. Okay, as there are two eigenvalues, then we will be having two eigenvectors. So first we will be finding by lambda 1 equals to 6, and that is our first eigenvalue. So whenever we will be putting lambda 1 equals to 6, so we will have this equation, and let's assume that our eigenvalue is nothing, eigenvector is nothing but a vector with 2 cross 1, because it will have 2 cross 1 order, so 2 cross 1 and 2 elements x and y. So just I have just solved with this elements x and y, and by this whenever you will be solving the equation, we will have two equations. One is minus 5x plus 2y equals to 0, and second is 5x minus 2y equals to 0. That is same thing. So just you will be arriving this, and if you will take let's take x equals to 2 or something. So if you will take x equals to 2, then your y equals to 5. So this will be your first eigenvector. Now what is the second eigenvector? Whenever you will be putting lambda equals to minus 1. So whenever we are putting lambda equals to minus 1, we have been arriving with this equation, that is y equals to minus x. So either you can put x equals to 1 or x equals to minus 1. So here I have put x equals to 1. So by that y will be equal to minus 1. So this is your second eigenvector. So we have two eigenvalues and two eigenvectors. So our question is there. Okay, so again I am repeating. First step is to find the characteristics equation. How the characteristic equation can be found? That is determinant A minus lambda I equals to 0. So we have found the characteristic equation. Once we find the characteristics equation, we can find the eigenvalues. Once we get the eigenvalue, we will put one by one eigenvalue. Whenever we will put one eigenvalue, we will be getting one eigenvector. Whenever we will be putting the next eigenvalue, we are getting the next eigenvector. So we got the eigenvalue and eigenvectors. So is it clear? Is this question clear to all of you? Clear, right? Okay, so now we will be revising some of the aspects of this linear algebra. So a set of vector belonging to R n space is called a basis if they are linearly independent, and every vector belonging to this Rn space can be expressed as a linear combination of these vectors. Okay. Now second thing is what are this linearly independent vector? A vector v1, v2, vn can be called as linearly independent vector if c1 v1 plus c2 v2 plus dot 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 cn vn equals to 0, only if c1 c2 cn all are 0. Okay, so that is the property of this property is known as linearly independent property of the vectors, that is linearly independent vector. So we can tell this v1 v2 vn are linearly independent vectors. Now where we are using this, for example, we have any data point. Okay, so we have okay, yeah, so for example, we have any data point. Okay, so we are expressing it in a coordinate system. Okay, so this coordinate system has two independent linear vectors, that is 0 comma that is 1 comma 0, that is the x-axis, and 0 comma 1, that is the y-axis. Okay, so we have two bases, that is x 1 comma 0 and y 0 comma 1. Now any point in this basis we can like a comma b, if there is a point like here, that is a comma b. Okay, a comma b, a comma b, this is a, okay, a comma b, then it can be expressed as ab equals to a into first basis, that is this basis 1 comma 0 plus b into 0 comma 1 basis. Further, if x and y are linearly independent, we can project this point AB in any basis such that this two bases are linearly independent. That is, C1 and C2 are linearly independent. So we can such that x and y are linearly independent. If x and y are bases, then x and y are linearly independent. So we can make any basis out of so we can project this point AB on any basis. Okay, so this is the concept. For example, if I tell you this, if we have a point this if we have a point AB, we can also project it. Earlier we have projected in this basis 1, 0 and 0, 1. We can also project in another basis 2, 3 and 5, 7. Why? Because this 2, 3 and 5, 7 are linearly independent. Okay, so that is why this 2 can form a basis. So earlier our basis was 1, 0, 0, 1, and now our basis is 2, 3 and 5, 7. So we can again project this in this basis. Why? Because this 2, 3 and this 5, 7, these two vectors are linearly independent. That is, it can only sum up to 0 if we have C1 2, 3 plus C2 5, 7 will be equal to 0, such that C1 and C2 both are 0. Okay, so this is the concept. Means any point like AB can be projected in a basis which are linearly independent. So that is the summary. Okay, we are generally projecting this point on the coordinate axis, that is the basis 1, 0 and 0, 1, but it can be projected in any basis such that these two bases are linearly independent. So this is the concept. Now why we are learning this? Okay, so this is the thing, like if we have so many points like z1 to zn, then we can project it in an independent basis like u1, u2, un, and we can calculate this alpha 1, alpha 2, alpha n. Okay, but the problem here is the time complexity. This is a Gaussian elimination. Okay, so this you can solve this x1 and x2 you can solve this, just you have to do that Gaussian elimination. Gaussian elimination is that thing you must have done in your this 8th class or 10th class. Just you have to solve this two equations. So by that you can get this x1 and x2. So similarly, by this Gaussian elimination method you can find this alpha 1, alpha 2, alpha n. But the problem here is the time complexity here is O(n) cube. Okay, this time complexity is a different domain, but you just understand this or just keep this as a fact that the time complexity of this Gaussian elimination is O(n) cube. Okay, so because it is a long equation, so the time complexity is O(n) cube. So the summary of this slide is we can project any point to any basis such that these bases are linearly independent, and by that we can calculate the coefficient like alpha 1, alpha 2, etc. here like x1, x2, etc. and we can project our point to that basis. Okay, so this is about linear algebra. So is it clear, this slide? Now the advantage of orthonormal vector forming a basis. Earlier the bases that we have seen like 1, 0 and 0, 1, these are orthonormal vectors. What are these orthonormal vector is? If we multiply this x dot y, then the answer will be coming 0. Okay, so that is what orthonormal basis. That means whenever we are doing the dot product or x, y, t, then the answer will come 0. So that is the orthogonal vectors. And orthonormal because these are unit vectors, that means the magnitude of these vectors are 1. Okay, so that is why this basis or the coordinate axis basis are orthonormal basis. Okay, that is why we prefer to project our data in a orthonormal basis. Why? Because you can see from this z is a point, that is a comma b, and now first we need to project it on two axes, that is u1 and u2. Okay, now the thing is this u1 and u2 are orthonormal basis, that is uyt means u1t you can say, and u2 into u2 will be equal to 0. That is the dot product of a normal orthogonal vectors are 0, and also as these are orthonormal basis, that is normal basis, that means the magnitude of this basis are 1. Okay, so u1 mod will be equal to 1. Okay, so this is the thing. Now why we are interested in projecting in a orthonormal basis? Because earlier we have to do the Gaussian elimination to find the coefficient like alpha 1, alpha 2, alpha n, or this x1 or x2. For finding this we have to put this Gaussian elimination method. But the Gaussian elimination method has a time complexity O n cube. Okay, now to find this alpha 1 and alpha 2, alpha 1 can be easily find out how. Alpha 1 is z of cos theta. Just projecting this z on this axis. So what is alpha 1? Alpha 1 is mod z into cos theta. Now if I find out this cos theta can be written as this. Okay, this is the angle between the two lines. Okay, so zt, if we have this zt and u1 divided by its mod. So this is angle between the two lines, that is cos of theta will be cos of the angle between the two lines will be equal to this. So solving this we are getting this zt into u1. Similarly alpha 2 can be found out by zt into u2. So this is the advantage of orthonormal vector forming a basis is we can directly find alpha by this product of z and ui. So our time complexity in this decreases to O(n) square. Earlier, if we if we form our basis in any vector which are not orthonormal, then the time complexity is O(n) cube. But now, as we are projecting our data to orthonormal basis, our time complexity decreases to O(n) square. So that is the advantage of orthonormal vector forming a basis. For this we have two theorems associated with this. The eigenvectors of a matrix belonging to this n cross n space having a distinct eigenvalues are linearly independent. Now if I combine the two concepts, first we have discussed regarding eigenvector and eigenvalues. Now all these eigenvectors of a matrix belonging to n cross n space having distinct eigenvalues are linearly independent. So these eigenvectors can form a convenient basis. Second thing is eigenvector of a square matrix are orthogonal. Okay, eigenvectors are orthogonal and eigenvectors are linearly independent, so it will form a most convenient basis. Okay, so this is the thing, the eigenvector of a square symmetric matrix can form a most convenient basis. So again I am revising. First what we have learned is what are these eigenvectors and eigenvalues. Second, we have what we have learned is linear algebra, the concept of linearly independent vectors in a linear algebra. That is, any point can be represented in a basis followed that this bases are linearly independent. And second thing, what we have seen, it is more convenient if these bases are orthonormal. That is whenever we will multiply these two bases, the product will be 0. Why? Because earlier if these vectors are not orthogonal, then what will happen is our time complexity to find the coefficient will be O(n) cube. But whenever we are having this orthogonal vectors or orthonormal vectors, our time complexity reduces to O(n) square. Now what we have seen is eigenvector are linearly independent. So that is the first thing. Eigenvector are also orthogonal. So by these two things we can easily summarize that eigenvector of a square symmetric matrix can form a convenient basis. Okay, so is it clear? Is this slide clear? Okay. Okay, now why we are interested in projecting our point on a suitable basis, that are the eigenvectors or whatever basis. So why we are interested? We are interested because of this thing known as principal component analysis. So principal component analysis. In principal component analysis, what we do, the eigenvector of a matrix with distinct eigenvalues are linearly independent. We have just seen the eigenvector of a square symmetric matrix are orthogonal. We have again seen that in this theorem, in the previous theorem. So PCA, or the principal component analysis, exploit the fact by representing the data to a new basis comprises of top k eigenvectors. That means earlier we may have 1000, yeah, this is only a 2D data, okay, 2D data. That means we are projecting it on a 2 axis, but originally our data can be on 1000 axis or 10,000 axis, like that. So we don't want that. We want to project our data into a more smaller number of bases. Okay, that is our idea. So that is known as principal component analysis. So earlier our data was projected in like 1000 or 10,000 axis. Now what we are interested to project our data in minimum number of axes. What are these axes? These axes are nothing but your eigenvectors. Okay, because we have just seen that eigenvector forms the most convenient basis. Okay, that is why we will be projecting to eigenvector. Second thing, we will take the top k eigenvalues. Okay, top k eigenvectors, and we will eliminate the other n minus k eigenvector. If there are total n eigenvector, then what we will do, we will only take top k eigenvector. We will eliminate the rest of n minus k dimension or n minus k eigenvector, because what happens is n minus k dimension will contribute very less to the data, or it will contribute very little to the reconstruction error. So this dimension we can just eliminate, and we can keep only the top k eigenvectors. So these are also the direction along which variance is minimum. Okay, so these are the direction in which variance is minimum. N minus k dimension which we are rejecting, these are the direction in which variance is minimum. How we know the variance is minimum there? Because eigenvalue is less in those direction. So that is why variance is minimum. Like here you can see in this graph, earlier we have this basis x and y. Now we want to project it into two bases, u1 and u2. Now you can clearly see that in u2 there is no variation in the data. Only we have more variation in data in this u1 axis. u2 we don't have much variation in data. It's just a little noise. You can see the variance is just here to here. So we have very little variance. So we can eliminate the u2, and we can project our data into one axis u1 only. So that is what we are doing in principal component analysis. So again I am telling, this u1 and u2 are nothing but your eigenvectors. We have seen that in this eigenvector we have maximum variance in data. This eigenvector we are not finding any variance of data so far. So we can just eliminate this axis, and earlier our data was in 2 axis. Now we can easily project our data only in 1 axis, that is u1. So that is what we do in principal component analysis. So the 3 interpretations of PCA that you have learned in your lecture is, it ensures that covariance between the new dimension is minimized. Now why the covariance between the axes are minimized? Because we know that we are projecting it on eigenvectors, and eigenvectors are linearly independent. So if vectors are linearly independent, then the covariance will be 0, or it will be very less. So that is the thing. Now second thing, it picks up dimensions such that the data exhibit high variance across this dimension. Now in this dimension we can see we have only picked u1 because in this dimension or in this eigenvector we can see maximum variance. And last is, it ensures that data can be represented using less number of dimensions. So earlier we are representing it in 2 dimensions. Now we have just eliminated 1 dimension. So we are projecting our data in 1 dimension. So these are the 3 different interpretation of PCA. Okay. Now example of reconstruction error. Now you will be telling that we are eliminating u2. So can there be any problem in the reconstruction? Whenever we are again reconstructing our data to our original data, will there be some error? Yeah, definitely there will be some error, but that error will be very minimum. For example, we can see by this example. So this is a data set, and now we are projecting it into two axes, u1 and u2. Now this u1 and u2 are nothing but eigenvectors that are given by this, and we have converted into a normal basis, so that is why we have just found out the unit vectors of this eigenvectors. So just found out the unit vector of this eigenvectors, and then what we will do, we will just like you can see, we will exploit this thing, that is the advantage of this orthonormal vector, that is alpha 1 will be equal to zt into zt into u1 or u2, whatever. So okay, yeah, so what we will do, we will find alpha 1 and alpha 2. Alpha 1 will be x transpose into u1, alpha 2 will be x transpose into u2. What is the x? X transpose into u2. X is not given here. Okay, yeah, this is the x. Okay, this is the x matrix, that is 3 x matrix or x vector 3.3 comma 3. Okay, this is the thing. So just you do the transpose, that is you write this x equals to this 3.3 comma 3, and that is xt, and you multiplied by u1. u1 is nothing but 1 by root 2 and 1 by root 2. You just multiply it and you will be finding this, and alpha 2 similarly you can find this alpha 2. So now we can again reconstruct it, and whenever you will be reconstructing it, that is alpha 1 into u1 plus alpha 2 into u2, you will be arriving in the same you will be arriving to the same x. Okay, so our reconstruction error here is 0 because we have utilized all the two principal components, but we have utilized all the two principal component. But the question is, in principal component analysis, what we do is we only take n minus k dimensions, we only take top k eigen vector, and we eliminate the n minus k eigen vectors. Okay, so here also what we will do is what we are going to reconstructing using fewer, that is k equals to 1. Earlier we have k equals to 2, that is we have two principal component. Now we will be reconstructing in using only one principal component, that is u1. So whenever we are reconstructing it by one principal component, we are arriving 3.15 and 3.15. So reconstruction error is here very minimum, because we can see here clearly that u1 does not have any variance of data. That is why we can just eliminate this principal component, and still we can get to a value which is very much same as our original value. So this is the example of the reconstruction error. Okay, so we can eliminate this n minus k eigenvectors and we can only keep the top k eigenvector, and then also our reconstruction error will be very less. So this is the idea of the principal component analysis. So is it clear? Okay. So now it will be better now it will be better if we can do this with the help of a code. So it will be better to analyze it, what I am telling. Hello?
Excuse me, sir.
Yes, please.
Can you show the previous slide?
Okay.
Sir, here first at alpha 1 we have taken x raised to t into u1.
Yeah.
Uh, but here the x bar here we are changing the x bar value and taking the x bar value as alpha 1 and u1, sir.
X bar value. X bar
That is
means
3.3 into 3.
3.3 into 3 is the, yeah, your x originally x is 3.3
3 into 3.
into, not into 3, 3.33. This is your
Okay.
original value. Okay,
Okay, sir.
then we have find out xt, that is 3.3,
Okay.
just transpose of this, and then we
Yeah.
have multiplied it by u1 to get the alpha 1 and u2 to get the alpha 2. Okay,
Okay.
and whenever we are doing this, x will be equal to alpha 1 u1 alpha 2 u2, same as this concept just we have discussed, same as this basis concept. Okay, like this,
Okay.
here we can see this x, if a is the x, so x will be equal to,
Mm.
here b is the x, so x will be equal to alpha alpha 1 u1 alpha 2 u2. Okay, like this, or you can see this for more more clarity. Z will be equal to alpha 1 u1 plus alpha 2 u2. Okay, plus dot 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 alpha and u2. Okay,
Sir, these eigenvectors can be solved using Gauss ideal method. Is it equal? We'll get the equivalent. What do you say? Eigenvalues or eigenvectors using Gauss ideal method.
Gaussian elimination,
No.
yeah, same
Hmm.
same you can get.
Either one we can use for PCA.
Yeah, either one you
The
can
EVA
use, but
method or even Gauss elimination method.
Gaussian elimination method is the common method. That means
Hmm.
you can solve any alpha 1 alpha n any
Hmm.
basis. Okay, any basis which are linearly independent, you can use that. But orthogonal, that is the complexity there is very much large. Like if you have if you have like two dimensional data, then alpha 1 and alpha 2 can be easily solved. But for example, you have n dimension data, for
Yeah.
that it will be very difficult to solve the alpha 1 alpha 2 alpha n, right? Because time complexity here is o n q. So for that, what we have done is we have tried with this orthonormal vectors. Okay, so orthonormal vector, if we are projecting our data into an orthonormal vector, then the alpha 1 can be calculated easily. That is the point transpose of the point into whatever that principal component. Okay, principal component vector, or principal component vector. And what we have seen is eigenvectors are linearly independent, eigenvectors are also orthogonal. So if we can change our eigenvector to an orthonormal value, that is just dividing it by its magnitude, so it will become orthonormal. It is already orthogonal. That is the
Yeah.
characteristics of the eigenvector. But if we can make orthonormal, then we just need to multiply this with the transpose of the point, and we are getting this alpha 1 alpha 2 etc. So it is more
Okay.
easier to us. So that is why we have changed to this. So this is the
So,
advantage of projecting your data into a basis that are eigenvectors. Okay,
sir, if our n is m dimensions, then our alpha will be of m alpha.
yeah. Alpha will be
Okay.
of m dimension only.
Okay.
Here
Thank you,
you,
sir.
yeah. So this is the thing. So is it clear to everyone what we have discussed so far? Any doubt up to this? You can ask me. Any doubt? Okay. Now, how to utilize this principal component analysis, that we will be seeing with the code. Okay. Now, there was a question in the chat box that Python code is asked in the exam or not. I don't think Python code will be asked in the exam. Your exam question will be very much similar to your assignment question. Okay, so I don't think you are getting any coding type of question in your assignment. So definitely you will be not getting any Python any question on Python code in your exam. But saying that, it is important to know how to code it, because any deep learning program you will be doing with the help of code only. Okay, you will not do by calculations. Okay, you will be doing with the help of code only. So that is why it is important to know at least how we are writing the code. Okay, so that is why I am providing code for everything. So after the class, just open my folder DL codes, and all the codes are there. You just copy the codes to your drive, see how the codes are written, and just run the codes, and you will automatically understand it. And also I have made sure that every code is self-explanatory. I have tried to put everything on the in the comments, so that the code is self-explanatory to all of you. Okay, is it clear?
Yes, sir.
Okay. Okay, so yeah, so this is the thing. So we are applying PCA on MNIST dataset. This you just ignored it. Yeah, this you just ignored it. So PCA we are applying on this MNIST dataset. What is this MNIST dataset? MNIST dataset consists of 70,000 grayscale images of handwritten digit from 0 to 9. Okay, and each image has a dimension 28 into 28, that is 784 pixels in total. Okay, so what we need to do is we will be projecting our data to some principal component, and we will be checking how many principal component we are needing to have so that the variance covered by our the variance will be completely or approximately covered by all our principal component. How many principal component we require to project our data, such that our reconstruction error is minimum. Okay, that we will see. So what you need to do is first just import the necessary libraries that is important for all the course. So just we are using NumPy, Matplotlib, this sklearn, that is scikit-learn library. This is a library very important for this machine learning. So this also we are importing, and we are fetching, and we are importing some of the necessary libraries. And then what we are doing is loading the MNIST dataset. I am not running this code. I have already run this code. I have already run this code before the class. I am not running this code because it might take a little bit of more time to load everything. So that is why I am not running this code. But every output is below the code, so there will be no issues. So yeah. So next step is we have to load this MNIST dataset. So again I am repeating, MNIST dataset is a dataset consists of 70,000 grayscale images of handwritten digit from 0 to 9, and each image has 28 into 28 pixel, that is 784 pixels in total. So what we need to do is we need to reshape into vector, because applying PCA what we need to do is reshape into vectors. Okay, so that so what we have done is we have reshaped all the pixel into vectors, that is 784 vectors. We have reshaped our feature. So this is the dataset MNIST.data, and then we have normalized the pixel. So in machine learning or deep learning, it is very essential to normalize your data, because there can be some feature in which the value is very high, and there can be some feature in which the value is very less. So what will happen is whenever the feature in which the value is very high, so our model will try to learn those feature well, and those feature in which the value is very low, our model will not learn those features well. So that is why a usual practice is to normalize the data. You know, pixel of a grayscale image is from 0 to 255. That means we have 256 values. Okay, so a pixel can take value from 0 to 255. Okay, so that is why we are dividing our data by 255. Why we are doing this? To normalize our data, or to get our data into a smaller subset. Earlier our subset is from 0 to 255, but now dividing our data by 255, we are just projecting our data to 0 to 1 range. Okay, so that is what we are doing in loading the data set. Next thing what is important is to center the data. Now what will happen is every data has some mean. Okay, we don't want the mean, because whenever we are putting the calculating the covariance vector, you can see that the covariance, the formula of covariance vector is 1 by n x minus mu transpose into x minus mu. Okay, that is the formula. But it will be easier for us if mean is 0. So that is why we are doing what we are doing is centering the data. That is, we are just subtracting the mean of the image, so that our data will have the zero mean. Okay, this ensures that data will have zero means and our covariance matrix will be easily calculated. So that is why we have centered the data. So two steps we have done. First, we have normalized the data, and second, we have centered the data so that mean is zero. And after that, what we have done is we are calculating the covariance matrix to capture the relationship between the features. Okay, because we have 28 into 28, that is 784 feature. Now what we are doing is we are finding the covariance matrix to capture the relationship between this feature. So this is our covariance matrix, that is 1 by n x transpose into x. So that can be calculated by this formula. We are doing all our coding in Python, so just by this formula np dot covariance x center dot t, we can find out the covariance matrix. Okay, this np is a numpy array. Okay, the library that we have just called numpy as np, so that is why np, and then this is the code np dot covariance, and then just put this and we can find the covariance matrix. Earlier we have matrix x centered, and now we have find the covariance matrix. After that, we have to perform the Eigen value decomposition. This is not Eigen value decomposition, so let me just we just have to calculate the Eigen value and Eigen vector. Okay, so we can say calculate Eigen vector and Eigen value. Okay. Okay, so this is the thing. So just we have to do is okay, just something like that. Yeah, so we have to calculate eigenvector and eigenvalues. Why we are needing eigenvector and eigenvalues? So eigenvector and eigenvalues are fundamental in principal component analysis. Eigenvector principal components define new axis with maximum variance. Eigenvalue indicate the amount of variance captured by each component. So this is the that is why we need to calculate the eigenvalues and eigenvector. Eigenvector are nothing but principal components in which we will project the data. Eigenvalues are important because the eigenvector which has more eigenvalue, it will capture more variance of data. The eigenvalues which the smaller eigenvalues will capture less variance of data. So principal component analysis, what we do, we take the top k eigenvectors and we eliminate the other n minus k eigenvectors. So that is why eigenvalues are important, because it indicates the amount of variance captured by each component or each principal component. So that is why we have to calculate the eigenvector and eigenvalues. So this is the formula to calculate the eigenvector and eigenvalues. So So this is the characteristics equation formula. What is this? This covariance into x into v equals to lambda dot v. So just we have discussed how we can find the eigenvector and eigenvalue. If we have a matrix A, so what we will write is A into eigenvector, that is, let's say eigenvector is v. So A into v equals to lambda into v, where lambda is the eigenvalue and v is the eigenvector. So now we have to find the eigenvalue and eigenvector of this covariance matrix that we have just calculated. Okay, so just we have to write covariance x into v equals to lambda into v. So by that we can find out the eigenvector and eigenvalues, that is lambda and v. So eigenvector, this can be done by only a single line of code, that is np line align dot eigen EIGH and covariance matrix. What our covariance matrix was, just put the covariance matrix as the argument and you will get the eigenvalues and eigenvector. Now we have to sort the eigenvalues and eigenvector of this line. Yeah, we have to sort the eigenvalue and eigenvector according to the indices. This is important. So just follow the code and then select the principal component, because we choose the top k eigenvector principal component. This represents the most important feature of the data. We select enough component to retain 95% of variance. So I have told you we want to retain such principal component which will retain retain almost 90 or 95% of variance. So here we are taking we are retaining that much eigen vector which will give us 95% of variance, up to 95% or greater variance. Okay, so that is our idea. So for that we have done this coding, and we can just find the number of components or number of principal components to get the 95% of variance. So cumulative, this is the formula, and by that we have find out that k where 95% of variance is retained. That means how many principal components are required to retain 95% of variance. So whenever you will run this code, this number of principal component to retain greater than 95% of variance, that is 154 principal component we require to retain 95% of variance. Total we have 784 component, that is 28 into 28, but now we can see that by utilizing only 154 principal component we can retain 95% variance of the data. Okay, so that is the idea of principal component analysis. That is, we need to project our data into principal components such that we do the dimensionality reduction. Okay, earlier we need 784 vectors to represent our data, but here by only 154 principal components we can retain more than 95% of variance. Okay, and then we need to do this reconstruction process. So this is the formula of the reconstruction process, and then we are just calculating the reconstruction error, and yeah, we are just calculating the reconstruction error, and we are just plotting a figure, and in this figure you can easily see that reconstruction error. What is the formula of reconstruction error? The formula of reconstruction error is the nothing but your mean squared error, that is 1 by n into sum of your original, that is y, minus y reconstructed, that is y hat whole square. So this MSE we just know, so that is the thing. So this, if I plot the reconstruction error with number of principal component, now when we have 20 principal component, for example, we are getting reconstruction error like 0.025. But whenever we are just adding principal component one by one, and we are getting to 154 principal component, then our reconstruction error decreases so much, or we are getting more than 95% of variance of the data. Okay, and then we just need to I have just compared the original image with different principal components. So this is the original image, that is handwritten. This MNIST dataset consists of handwritten digit. So this is the original image, that is 5 written. But on the first principal component we are getting so much reconstruction error, that is why this is not clear. Whenever we are putting 5 principal components, so this is the reconstruction error, less reconstruction error than one principal component. 10 principal component less than 5, then 20 principal component less than 10, then 50 are somewhat our 5 is appearing, and 154 5 is appearing very well. That is, our reconstruction error is very less, or we are covering more than 95% of variance. So that is why after putting 154 principal components, our digit is appearing like the original image with very less reconstruction error. So total we have 784 principal component, but by 154 principal component only we are getting the image very closer to our original image. So what we have done is, we have done this dimensionality reduction. Okay, so is it clear what I have told? What was our idea, what I have told? Is it clear? Am I audible?
Yes, sir.
Yeah, any doubt, anyone? What we have done, what was our idea?
Sir,
Yeah, please.
the principal component, the line graph, whatever you have shown, it
Yeah,
varies from one program to another program, sir. For example, this one.
yeah.
If the, for example, I have already solved this, but it's showing not exactly this line. It's showing little bit tilted.
Okay, no, principal, we have, we are just doing this equation, right? We are computing our reconstruction error by this equation. So
Yes, sir.
it should come same for everything.
No, sir, it's not exactly the same, but it is similar. We can say it
Okay.
is not exactly, but it's similar.
Okay, so might be your what can be the reason? Might be the principal components it is choosing 95% of variance. It might choose some other principal components, so that can be the reason, I think,
So it may
because
vary, sir, then.
it can vary very slightly, but it should not vary much, I think.
And no, sir, it's not
Uh,
much varied, but it's slightly varied.
okay, so it should come very similar to this, because formula we are applying the same, right? It
Yes,
is
sir.
just that how many number of principal component it is retaining. Is it 154 only?
No, sir, it is 156.
Okay, so that is why that may be the reason for this. Okay,
Okay.
yeah. So 95% of variance of the data. Hello.
Sir?
95% of variance of the data you have covered by your PC.
Maybe, sir.
Okay.
I was clueless about this, so I'm asking.
Okay. No, I am asking what is the value here. Is it 0.95 or more than that or less than that? It should be, I think, less than that.
It's 95 point something. I
Okay.
don't remember.
Okay. That is why I think there is a difference in our results. Okay.
Okay.
Okay. Yes, Jayant, any doubt? Can we get the link to this collab node? Yeah, this link I have already given, right? This you all know, right? Where is this code?
Hello, sir.
Yes, please.
Yeah, so I have some doubt about the
Yes.
projection of these vectors.
Yes.
So the process, have you explained basis vector already?
Yes, I have explained already. I have explained the basis, right?
Yeah, so where can I see that here? Because on top of that only we calculate region vectors, right?
Basis are nothing but your principal components, right? So you want to see the principal components also.
Okay, we derive basis vector based on
This is
the.
the formula to get the principal component and this sorry eigenvector and eigenvalues, right? Where is the formula? This is the formula, or this is the code.
Okay.
Yeah, so by this
So,
we are getting eigenvalues and eigenvectors. Our principal components are nothing but top k eigenvectors. So it will choose the top k eigenvector. How it is choosing the top k eigenvector? Such that it covers more than 95% of variance. So we can see this by 154 principal component we are covering more than 95% of variance. So 154 principal component we are keeping, other we are eliminating. Okay.
and where exactly we are projecting, there is some projection.
Projection are on the this eigenvectors, right? That is why we are calculating eigenvectors.
Okay, internally it will be projecting it along with some axis, right?
Yes, so that axis is nothing
Orthogonal
but,
axis.
yeah,
Or
that axis are nothing but your eigenvectors.
okay, got it.
Okay,
So
so
internally this method itself will be doing that. We know that.
yeah. This code only will do this. This is the line, right? By this line we are calculating the eigenvectors and eigenvalue of the covariance matrix. Okay, this is the covariance matrix. Where is the covariance? Yeah, this is the covariance matrix.
Okay, and that mean and standard deviation we are calculating for each of the.
Mean, see, we have centered the data. As we have centered the data, so that is why mean is 0. So that is why we have arrived to this formula, x transpose into x. Otherwise, what is the covariance? Covariance is 1 by n into x minus mu transpose into x minus mu, right? But as we have centered the data, so that is why it is only x transpose and x.
Okay.
Yeah,
So we have to mean center it so that the origin it will come to origin.
and also
Not it in the xy coordinate. Yeah, that if I want to visualize it in the coordinate system.
visualize this in coordinate system. As we have 154 coordinates, so it can't be uh, we can't visualize the data. That is the thing, right?
Okay, okay, got it. Yeah. Thank you.
Okay, so yeah, some people are new here. I think. Do we need to standard deviation for equals to 1 for all feature? As we are doing this step, that is where is the step? That is we are yeah, we are standardizing or normalizing the data, so we don't need to do ensure the standard deviation equals to 1, because we have already done this step. Okay, that is normalize the pixel value. That is our range will be between 0 to 1, so we don't need to think about this standard deviation. Okay, clear, right? Okay, I think some people are new to this class, so let me show you again. Yeah, so let me share my entire screen. So everyone know this folder? Do everyone know this folder? Am I audible?
Yes.
So who was asking? Yeah, who was asking? Jayant Yadav. Do you know this folder, Jayant?
Sorry, sir, no, sir.
You are not audible. Can you please increase your volume?
Is it audible now?
Yes, now it is audible. Audible. So do you
Uh,
know that folder? What I have just shown? This folder.
no, sir. Can you please share that link?
Okay.
Sir, it will be get from the weekly reports where we get the updates. There is there, sir, in the
Yeah,
last bit.
yeah. They're also there. So this is the folder link. Okay, where you can have my where you can have my this all this presentation as well as the code. Okay,
Okay,
and
thanks.
another thing is let me share that if I have. Another thing is this spreadsheet is very important. Okay, this is the spreadsheet. It is very important. Okay, this is the spreadsheet. I am again marking it. So let me, yeah, so this is the spreadsheet. So whenever you will go to the spreadsheet, what you will see is you will see content of 4 TAs. So 4 TAs are taking this course, and my content is at the bottom because I am taking the class on the last day, that is Tuesday. Other TAs, one TA I think is taking class on Friday, one on Sunday, one on Monday, and I am taking my class on Tuesday. Okay, so this is my presentation folder link. Either you can go here and have the all that presentation and etc. The folder I have just shared, or you can just directly go to this link I have shared. So that also you can do. And another thing, these are the YouTube links. Whatever class I am taking, all this will be available to a YouTube channel. So you can just go to any video. You can just subscribe the channel and you can get the update. Otherwise, you can again come to this spreadsheet and you can open the video one by one. Okay.
Yeah, thanks, sir.
So these two links are very important. So keep the students. Okay. Bookmark the student. Okay. So let's move on to our discussion section. Yeah. So what we have discussed? We have discussed eigenvalue, eigenvector, then linear algebra, then this principal component analysis. Now we are remain with two things. One is called eigenvalue decomposition, and another thing is called singular value decomposition. So how to calculate this eigenvalue decomposition and how to calculate this singular value decomposition. So this is the eigenvalue decomposition. So what is eigenvalue decomposition? Eigenvalue decomposition, it is a method used in this linear algebra to break down a square matrix. So it is very important, and eigenvalue decomposition can only be done with the square matrix only. Okay, so if we don't have matrix which is not square, that is it has dimension m cross n, so we cannot use this eigenvalue decomposition there. So what does this eigenvalue decomposition does is it converts the square matrix, it breaks down into simpler components called as eigenvalues and eigenvectors. So that is the task of this eigenvalue decomposition. So this decomposition is significant because it transforms matrix operation into simpler scalar operation involving eigenvalues, making computation easier. Okay, so what we are doing is, as we are converting it to eigenvalues which are scalar, so what we are doing is we are making the computation easier. So mathematically, if I told you, this is the formula to get the eigenvalue and eigenvector. Now how we can do the eigenvalue decomposition of this matrix A? How we can do is, the eigenvalue decomposition can be done by this formula: A equals to V lambda and V inverse. So what is this V? V is the matrix of eigenvectors. What is this lambda? Lambda is the diagonal matrix of eigenvalues. And what is this V inverse? V inverse is the inverse of this matrix V. So that is the thing. So again I am repeating, what we are doing is, we have a square matrix, that is A. What we are doing by eigenvalue decomposition is breaking the matrix into simpler matrix involving eigenvectors and eigenvalues. Okay, so how we are breaking it? We are breaking it by V lambda V inverse. What is this V? V is the vector containing eigenvector column wise. Like this, if you have x1 y1 as your first eigen vector and x2 y2 as your second eigenvector, then this will be the V matrix. Okay, that is the matrix containing eigenvectors. What is lambda? Lambda will be eigenvalues. So we will have two eigenvalues. If we are doing our calculation on 2 cross 2 matrix, then we have two eigenvalues. So our lambda will be diagonal matrix containing eigenvalues. So that will be lambda 1 and lambda 2, and other elements will be 0 because these are the diagonal matrix. So this is your lambda vector. This is your V vector. This is your lambda vector, and V inverse can be calculated. Okay, inverse you all know how to calculate. You have to do the cofactor, and then you have to find the cofactor matrix and then divide it by the magnitude, and you can get the this inverse of the matrix. Okay, so this is about eigenvalue decomposition. There is another thing called as singular value decomposition. Now again I have told you, this eigenvalue decomposition can only be applied in case of square matrix. But what happens if our matrix is not square? That is, our dimension can be, here our dimension should be always m cross m. Okay, that is square matrix. But what if our dimension is m cross n? That is rectangular matrix. So this singular value decomposition generalizes the eigenvalue decomposition of a square matrix with an orthonormal eigenbasis to any m cross n matrix. So the eigenvalue decomposition can be done only on this square matrix, but this singular value decomposition can be done for m cross n matrix, that is any rectangular matrix. So what is the formula of this? This is the formula of this. If we have a vector A, it can be written as u sigma vt. So this is very similar to this. Okay, if you compare this and this is very similar. What we are doing is, if you can see this, if this sigma will represent this lambda, this as we have the square matrix, so it will be V inverse. So here you have u and vt. Why you have two things, u and vt? Because you have different set of dimension. One dimension is m and the dimension is n. So that is why you will have two matrices. One is u and the one is vt. So what is this u? U is a m cross m. Okay, m cross m. If our matrix is m cross n matrix, A matrix is m cross n matrix, then our u matrix will be m cross n orthogonal matrix whose columns are left singular vectors of A. What is this? We will be seeing in a sample question. What is this lambda? What is this sigma? Sigma is very close to this lambda only. Only difference here is sigma will be a diagonal matrix only, but it will have earlier in this lambda matrix we are putting in the diagonal, we are putting the eigenvalues. Here we will be putting the singular values. What are singular value? Singular value are nothing but square root of eigenvalue. So what will be the square root of this u matrix? if we just root it, we will be getting this singular values, and then we have to just put it in like this, and we will be getting a sigma matrix. And what is this VT? This is the transpose of n cross n orthogonal matrix. So earlier it was m cross m, now it was n cross n, because here we have two dimensions. Earlier we have only one dimension, that is m cross n, that is why v and v inverse. Here we have two dimensions, one is m and the one is n, that is why u will have consist of m cross m, and vt will consist of n cross n orthogonal matrix, where the columns are right singular vectors of A. So this I will be explaining in the question only, but this is the difference between the eigenvalue decomposition and singular value decomposition. So is it clear by the formula? Okay, so let's solve a sample question, it will be more clear to you. So this is the question: perform the eigenvalue decomposition for this matrix. Okay, so this is the matrix 4 1 and 2 3. Okay, so we have to do the eigenvalue decomposition. What does eigenvalue decomposition means is, we have to convert it into then this lambda and this V inverse. We have to find this three matrix. So we have this matrix A, and we have to convert into this three matrix, that is V, that is a vector, that is a matrix containing all the eigenvector. V inverse is the inverse of the V matrix, and lambda is the diagonal matrix consisting of eigenvalues. So we have to find this three matrix. That by that we can perform this eigenvalue decomposition. So how to do it? Very simple. Again we have to find the characteristic equation of the matrix, that is A minus lambda I det, determinant of that, and calculating it. This is the characteristics equation. Whenever we will be solving this, the equation that we'll be having is characteristics equation of the matrix. So this is the characteristics equation, and just factorizing it, and we can find out this two values of eigenvalues, that is lambda 1 and lambda 2. Lambda 1 is 5, lambda 2 is 2. So after this, it is very easy to it. So what will be a diagonal matrix then? It is very easy. A diagonal matrix will be 5 comma 5 2 and 0 0. So this will be a diagonal matrix. So we got this matrix. Okay, now we have to find V and V inverse. V can be calculated. V is nothing but a matrix consisting of eigenvectors. So for that, putting lambda 1, we will be calculating eigenvector. So putting lambda 1, we are getting a eigenvector 1 comma 1 1, and lambda 2 equals to 2, we are getting a eigenvector 1 minus 2. So what will be our V? Our V will be 1 1 and 1 minus 2. So we calculate lambda, we calculate V, and just we have to do the inverse of this. Inverse of this very easy, because it is a two-dimensional matrix. So just have to do the cofactor, and then divide it by the det of this, and you will get the inverse. So just I have done the cofactor. Cofactor, I hope you all know what is cofactor. Cofactor is nothing but if I consider the 2 cross 2 matrix, then cofactor is diagonal value of the of this entity, that is minus 2, and what you have to do, minus 1 I plus j. I plus j is the index of the element. So if I do the index of this element, that is 1 comma 1 plus 1, so 1 plus 1 is 2, so 1 minus 1 square is 1 only. So this element will be minus 2 only, and then you can find out the cofactor matrix for all the index, and then just divide it by that magnitude of this vector, and you will be getting the inverse. So we got the lambda, we got the V, we got the V inverse, and by this what we have done, we have completed the eigenvalue decomposition of A. Okay, so is it clear to all of you?
So just one question. I think I missed that.
Yes.
Uh, so so we calculate PCA. So where exactly this step is required?
PCA, see, whenever you are calculating the eigenvalue and eigenvector, right? So in that step you can easily apply this, okay, to have a more simpler calculation. So instead of doing all this A lambda, V lambda, etc., you can also do the calculation with eigenvalue decomposition, because eigenvalue decomposition will give you eigenvectors as well as eigenvalues. Okay. The
So
lambda.
you mean to say this is the alternative option?
Yeah.
Okay.
But
Okay.
as we are doing by a Python code, so just we need to write a code, so this does not have any major significance there. Okay.
Just for understanding purpose.
Yeah.
So we may have two option in Python code, na, like this
Yeah,
means
if
this.
you are just writing the matrix and do all the operation step by step, then you can apply this. But as we are doing by a Python code with a library called numpy, so just one in one line of code we can get the eigenvalue and eigenvectors. Okay.
Okay, but then if we perform both the operations, so how can we check that which one is better?
Which one is better? Which one is better? As we are doing Python code, this is more better, right? Because it is giving you both the vector of eigenvectors and as well as eigenvalues. So this is more better, I think.
So is that similar to the singular value decomposition? Because that
Yeah,
term.
singular value decomposition, same thing, only this eigenvalue decomposition is applied for m cross m or a square matrix. Singular value decomposition can be applied for m cross n matrix, which is not a square matrix. That is, singular value decomposition is applied for rectangular matrix. Okay.
Okay, yeah.
Okay,
Okay,
so
got it.
let's solve for a singular value decomposition also. This will be more better clear. So perform singular value decomposition for A equals to this. Okay, so we have a matrix of 2 cross 3 order. Okay, 2 cross 3 order, we have a matrix and we have to perform a singular value decomposition. Okay, so singular value decomposition, first, yeah, let me show you in the formula that what is U? U are M cross M orthogonal matrix whose columns are left singular vectors of A. So to get the orthogonal matrix, what we have to do is we have to multiply the matrix with its transpose. By that we can get the orthogonal matrix. So that is why A dot AT. Okay, and we have to yeah, this is an order M cross M. Okay, if you have M cross N vector, this is the order of M cross M. So that is why we are doing AAT, not ATA, because whenever we will be doing AAT, then what will be the order of the matrix? 2 cross 3. Okay, 2 cross 3 into 3 cross 2. Okay, 3 cross 2. So this will be a cancel. So our matrix will be from 2 cross 2. Okay, so we want M cross M matrix. That is why we are doing AAT, not ATA. So this is the idea. So just we have to compute the we have to compute AAT, and when we are computing AAT, this is the AAT. Now find the eigenvalues of yeah, we can find the eigenvalues of AAT, that is lambda 1 and lambda 2. So yeah. So lambda 1 and lambda 2, we have find the eigenvalues, and what will be our this singular, yeah, we are converting it into u sigma and vt, right? U sigma vt. So how we can find the sigma? Sigma can be found out by root over the eigenvalues. Okay, singular values are nothing but square root of the eigenvalues. So just square root of the eigenvalue and you will get the singular value, that is represented by sigma 1 and sigma 2. And then you have to put it in the matrix form, diagonal matrix form, and this is the diagonal matrix. Now the question can be, why it is not a 3 cross 3 diagonal matrix? Because you see in the formula, our u will be our A will be formed by, yeah, our E, which is a m cross n matrix, will be formed by u, that is a m cross m matrix, and if we do the sigma with m cross m, then our matrix will be found by m cross m only, but then we cannot multiply it by vt, that will be found by n cross n. Okay, so for that we have to make this singular value matrix as m cross m. Okay, so whenever we will multiply m cross m with m cross n, this m will eliminate and we will be getting m cross n matrix. So that is why a singular value matrix will be ordered 2 cross 3 or m cross n only. So this is the idea. So we have got the singular matrix, that is sigma. So we have got the sigma. Okay, yeah, this is sigma. Okay, this is sigma. So we have got the sigma. Now our next step is to calculate the u. So how we can calculate the u? Again we have to find the eigen vectors. again we have to calculate the eigenvectors. So taking the lambda 1 value as 25, we are calculating the first eigenvector, that is x equals to y. So we can take one, but here it is important to know that always what we do is we do the unit, we always calculate the unit eigen vector. So that is why we have put the square root 2. So that is why this is the eigen vector u1, and again we can calculate the eigen vector u2 also. So by that we are getting the u vector. Now similarly we can get the v vector. How we can get the v vector? Very same, only the difference is earlier we have done A80 because we want the matrix 2 cross 2. Now we want a matrix 3 cross 3. That is why we will be multiplying 80A. Then again we have to find the lambda 1 and lambda 2 for this matrix, and we can find the u1 and u2 for this, and u1, u2 and u3 here for this, because we are calculating for 3 cross 3 matrix. So this is the vt matrix. So we got the u matrix, we got the sigma matrix, we got the vt matrix. So this is the full singular value decomposition. So this is the singular value decomposition. Okay, so is it clear to all of you?
Sir, why x equal 1 upon under root 2 and y equal 1 upon under root 2? Why we choose this value?
See, x, it will be convenient if we choose x equals to 1 and y equals to 1, but here always in this SVD what we do is we choose our eigen vectors to be unit vectors. Okay, so that is why to convert this eigen vector into a unit vector we have done this root 2 here. So you can write your u1 as 1 1, but you have to convert this into a unit vector. So to convert it into a unit vector you just have to divide it by its magnitude. What will be the magnitude of it? That will be root over 1 plus 1. Okay, 1 square plus 1. So that will be 1 plus 1. So that will be what will be your this unit vector?
Under root 2.
1 by under root 2 and 1 by under root 2. Okay, so this is
Oh,
the idea.
okay.
This is the idea. So that is how you have done the singular value decomposition. Okay, clear, right?
Sir,
Yeah, please.
sir, the value of u should be positive, 1 should be the negative. The value which is positive in that is fourth element should be negative, and all elements should be positive according to the above values.
Can you please repeat? I'm not getting what you are telling.
Sir, here in the solving minus 8x plus 8y equal to 0,
Yeah.
we got the x is equal to 1 by root 2 and y is equal to 1 by root 2.
Yes.
Yes. Then we combining these u1 and u2 in u.
U1 and U2 in U. U1 and U2 in U combining. Okay. So this matrix. Yeah.
Yeah.
Yeah. Okay.
Uh,
So you are telling why it is
the
minus
number
minus.
should be positive.
Okay. So there can be a mistake here. So this can be positive, this can be positive, or this can be negative also. Whatever you will tell. So let's make this positive. That is plus plus, and then this also can be done as plus and minus. Okay.
Yeah.
Okay. That can be done. Okay.
So then the whole value is going to change.
No, whole value will not going to change. You can do
Then
the
no,
calculation also.
positive and negative values.
Positive and negative value here also, right?
Yeah.
Here also this is same thing, right? You only. So
Sir,
here
if
also
that changes, then the summation of what is AU transpose of V is also going to change its value.
no, you can perform it. It will not change because this is a diagonal matrix, right? So it will not change. You can perform it. You can perform by
Okay.
plus and minus also, and you can see the same results. Okay. Just take care that it is a unit vector. Okay.
Okay.
So is it clear to all of you?
Yes, sir.
Yes, sir.
Okay, so by this we will be moving on to our question
Yes.
answer. This week question answer based on this eigenvalue, eigenvector, linear algebra principal component analysis, Eigen Value Decomposition and Singular Value Decomposition. Okay, so this is the first question. Kindly everyone first guess it, and then we will discuss the question, discuss the solution. Okay, so which of the following is a measure of the amount of variance? Okay, amount of variance explained by a principal component in a PCA. A is covariance, B is correlation, C is mean absolute deviation, D is the eigenvalue. So any guesses for this? Here D. Anyone with any other guesses apart from D? Okay, so no other guesses. So yeah, absolutely right. That eigenvalue is the right answer. So in principal component analysis, eigenvalue represent the amount of variance. Okay, explained by the principal component. We have just seen in our code also, a larger eigenvalue means corresponding principal component capture more of the variance in the data set, and we will only keep the top k eigenvector whose eigenvalue will dominate. Okay, so option D is your correct answer, that is eigenvalue. So is it clear to all of you? Eigenvector will give the direction of the principal components. Eigenvalue will help us to understand that in which principal component our maximum variance is captured. Okay, so these are the two things. Now what is the limitation? What is the limitation of PCA? It is computationally less efficient than autoencoder. Okay, this is an autoencoder question. So it can only reduce the dimensionality of dataset by a fixed amount. It can only identify the linear relationship in the data. It can be sensitive to outliers in the data. So any guesses for this? Just remove this option. Okay, we will discuss in the next class about the correlation of this PCA and autoencoders. We will be discussing this question on the this option in the next class. You just answer between B, C and D. Okay, so what is the correct answer between B, C and D? C and D. It can only identify
D.
linear relationship of data, and D, it can be sensitive to outliers. Okay, D, it can be sensitive to outliers. Okay, so sensitive to outliers is very true, because if there is an outlier which is giving which is indicating more variance to a principal component, but it is an outlier, so it can baffle your principal component. Okay, so option D is right. And next thing is it can only identify linear relationship in data. So in PCA, what we are doing is alpha is calculated by this xt into our mean. Okay, xt into u1, u2, etc. u1 and u2, etc. are nothing but the principal component. So what we are doing it can only identify linear relationship of the data. Okay, and it can be sensitive to outlier. Just I have told you that since PCA is based on variance extreme values outlier, it can disproportionately influence the principal component, leading to misleading result. Like one point is outlier, because of that one point you can consider that acts as your principal component, but that is not among the k top principal component. So it is very sensitive to outlier. So option C and D are correct. Other option, let's not discuss that. It can reduce dimensionality of data to a fixed amount. That is not true, because yeah, that is true to some extent, because it can only reduce your number of principal component to a fixed amount according to your value of the eigenvalues, or according to a dominant eigenvalues. So this is somehow correct, but here it is written it can only reduce and correct the number of principal. Number of principal component can be a hyperparameter, like just we have chosen for 95% of variance. So that is why for that it has been told that it is not the right answer. Okay, so this is the thing. So option C and D are correct answers. Okay, so this is the thing. Is it clear?
Okay, sir.
Which of the following is a property of eigenvalues of a symmetric matrix? Eigenvalues are always positive, eigenvalues are always negative, eigenvalues are always real, eigenvalues can be complex numbers with imaginary part non-zero. So any guesses for this? C is the correct answer, right? For a symmetric matrix, that is a square matrix A where AT equals to A, the eigenvalues are always real. This is a fundamental result of the linear algebra. Symmetric matrices are orthogonal and have real eigenvalues, so these are the characteristics of a symmetric matrix. Okay, so which makes them important, like application like PCA where covariance matrix is symmetric. So this is the thing. So eigenvalues are always real for a symmetric matrix. So this is the thing. So option C is the correct answer. These questions are very much fundamental to your eigenvalues and eigenvectors, etc. So let us move to the next question.
Sorry, why it is not the complex number?
This is the characteristics of a symmetric matrix. Okay, so this is fully related to your mathematical part. So you can
Okay.
just revise your eigenvector, eigenvalues, and then this
Okay.
is the thing. Okay. So the eigenvalue of A are 3 and 4. Which of the following are eigenvalue of AQ? Again a again a question very much related to this eigenvalue concept. So if you have a matrix A and its eigenvalues are 3, 4, 3, 4, which of the following are eigenvector of AQ? So C, someone is telling C. Yeah, absolutely right. So this is basically a theorem. If a matrix A has eigenvalue lambda 1, lambda 2, lambda n, then if we are finding the eigenvalue of AK, then our then our eigen value will be lambda 1k, lambda 2k, and lambda nk. So our eigenvalue for A was 3 comma 4, so AQ will be equal to, our eigenvalue of AQ will be equal to 3 cube. 3 cube is 27 and 4 cube is 64. So option C is your correct answer. Okay, so this is related to the diagonalization thing. So diagonal matrix, whenever we are writing this diagonal matrix, this is lambda 1, lambda 2, etc., like lambda n, etc. So in diagonal matrix, what is the property of diagonal matrix? Whenever we are doing the power of a diagonal matrix, all the eigenvector will be will be powered by same number as the diagonal matrix. So it will be lambda n. Okay, lambda n. Okay. So this is the thing. So again a very fundamental question related to eigenvalues. Now fifth question, if we have a matrix 12 cross 12 matrix having entities from R, what is the maximum number of linearly independent eigenvector corresponding to real eigenvalues possible for this matrix? So any guesses for this important question? Yes.
So I don't have this question. Assignment 5, no?
No, I am not solving your assignment question. I am
Okay,
solving
okay.
questions similar to your assignment, so that
Acha, acha.
whenever you will be solving the assignment, you will not feel something new. Okay, that is my duty. Assignment you have
Okay,
to
okay.
solve by yourself because it is
Okay.
graded. Okay, got the concept?
Yes, sir.
Okay, so that is the thing. So if we have a 12 cross 12 matrix having, yeah, so you just know that we have a matrix of m cross m, then how many eigenvalue it will have? It will have how many eigenvectors it will have? It will have m eigenvectors, and these eigenvectors are the maximum number of eigenvectors. So this is the concept, like you can see in our question, like we have solved for 2 cross 2 vector, right? Yeah, we have solved for 2 cross 2 vector. So for 2 cross 2 vector, how many eigenvector we are getting? We are getting 2 eigenvector, v1 and v2, right? So for m cross m matrix, how many eigenvector we will be getting? We will be getting m eigenvalue and m eigenvectors. So these are the maximum eigenvector you can get. Okay, so these are the maximum number of principal components also that you can project your data on. Okay, so again I am repeating, the question can be a little reverse, like how many maximum number of principal component can be we can have for 12 cross 12 matrix. So our 12 cross 12 matrix, maximum number of principal component can be 12. Okay, so this can be also the question. So option C is the correct answer. Okay, so 12 number of linearly independent eigenvectors. So option C is your answer. A, C and D, A, C and D, A, C and D. Here in the question it has been told maximum number, okay, maximum number of linearly independent eigenvectors. So if it was asked not maximum and number of linearly eigenvector, then you can go with all of this A, C and D. Okay, but as in the question it has been asked maximum number of linearly independent eigenvector, then option C is the correct answer. Okay, clear, right? Maximum is 12. Okay. Now question 6 to 9 are based on this data, and this is the data. x1, x2 and x3 are three column vectors. x1 is 2 2, x2 is 1 2 and x3 is 2 1. So we have to answer a question based on this input. Okay, so what is the mean of this given data point x1, x2 and x3? Okay, x1, x2 and x3 are nothing but your data point. So what is the mean? How we can calculate the mean? Mean is x1 plus x2 plus x3. Okay, plus x3 by 3, that is the mean. So just you have to add this 2 plus 1 plus 2, that is 2 plus 1 is 3, that is 5. Okay, and 2 plus 2, 5 by 3, 5 by 3 will be your answer. So what is 5 by 3? 5 by 3, 5 by 3, 5 by 3 is your option B. So option B will be your answer. Okay, so 5 by 3, 5 by 3 will be your answer. So option B is your answer. Okay, so clear, right? Not D but B. Okay, 2 plus 1 plus 2 is 5, 2 plus 1 plus 2 is 5, and we have to divide by 3, so 5 by 3 by 5 by 3 will be your answer, and 5 by 3 is 1.67. Okay, so option B is your answer. Is it clear to all of you how we are finding mean?
Okay, sir.
I think it is clear. Yeah. Then the covariance matrix, this is the covariance matrix, and what is the covariance matrix? Okay, so covariance matrix, we have to do this calculation. We already got the mean. Okay, what was the mean? Mean was the 5 by 3, 5 by 3. So x bar we know, x we know, x bar we know, and again we can calculate this, that is x minus x bar for all the 3 data point. Okay, because here sigma is there. What is this sigma? Sigma is summation for all the data point. So that is why I am calculating x1 minus x bar for the first data point, x2 minus x bar for the second data point, x3 minus x bar for the third data point. Now what I will do is I will add all this, because our covariance is sigma I equals to 1 to n xi minus x. Yeah, then what we have to do is we have to find out this x minus x x bar transpose. What will be the transpose? Transpose is nothing but 1 3 1 3 in a row, and x this for minus 2 by 3 1 by 3 in a row, and here 1 by 3 minus 2 by 3 in a row. You just multiply it and you will be getting this result. Okay, your x1 minus x bar and x1 minus x bar transpose will be equal to this. This will be your x2 minus x bar, x2 minus x bar transpose. This will be your x3 minus x bar, x3 minus x bar transpose. So we have by this we and just we if we add all this, so we will be getting this, and then we have to divide by n. N is the number of data point. So just I have just added it and then divided by 1 by 3, and this will be your answer. 2 by 9. 2 by 9, what is 2 by 9? 2 by 9 is 0.22, right? Yeah, 0.22. 1 by 9 is minus 0.11. 1 minus 1 by 9, that is minus 0.11. 2 by 9 is 0.22. The option A is the answer. Okay, is it clear? Simple calculation, very simple calculation. Is it clear how to find a covariance matrix? Clear, right?
Yes, sir.
Yeah. Okay, so the maximum eigenvalue of the covariance matrix C is, so we got this covariance matrix, that is 2 by 9 minus 1 by 9 minus 1 by 9 2 by 9. Now we have been told is what is the maximum value maximum eigenvalue of a covariance matrix. So how many eigenvalue we will be getting from this matrix? How many eigenvalue we will be getting from our covariance matrix?
4.
Yeah, 2. 4, not 4, 2, right?
Right.
Yeah, two eigenvalue will be getting. So what is the maximum of these two values? So we have to again form a characteristic equation for this, that is c minus lambda I, that of c minus lambda I equals to 0, and we will be arriving with this equation. Okay, this is our characteristic equation. Just factorize this and we will be getting two cases. 2 minus 9 minus lambda equals to plus minus 9. First take with plus 1 by 9, and we will be getting a value that is 1 by 9. Then solve with minus 1 by 9, and whenever we will be taking minus 1 by 9, then you will be arriving to this, okay, that is 1 by 3. Lambda 2 will be 1 by 3. So lambda 1 is 1 by 9, lambda 2 is 1 by 3. Here you have to find the maximum eigenvalue. So maximum of lambda 1 and lambda 2, which is maximum? Lambda 2 is the maximum, that is 1 by 3. So 1 by 3 will be the answer, that is option A. Okay, so is it clear? Is it clear?
Yes, sir.
Now the eigenvector corresponding to the maximum eigenvalue of the given matrix C is, now we have to find out the eigenvector corresponding to the maximum eigenvalue. Okay, so maximum eigenvalue we know that is 1 by 3. Now eigenvector corresponding to this eigenvalue, how we can find? We can find by this equation. C minus lambda v equals to C minus lambda I into v equals to 0. By that we can find the v1. Okay, so C minus lambda, the lambda max is 1 by 3 from our previous question. So C minus lambda into v equals to 0, we can find the v. So yeah, v is coming x equals to y. That means it can take any proportion of 1 comma 1 vector. So k into 1 1, that will be your answer. Now k, according to our question, we can adjust k. So if k equals to 0.71, then this is the answer. If k equals to 1, then D is your answer. So option A as well as option D is the answer. Okay, so is it clear? Now this is the last question. What is the determinant of 2 cross 2 matrix that has eigenvalue of 4 and 5? Again, a basic question of eigenvalue and eigenvector. So det of any matrix or determinant of any matrix is given by the product of their eigenvalues. Okay, why? Again, this is because of the diagonalization of matrix. So diagonalization of matrix, your product will give the det of the matrix. Okay, so that is why the determinant of a matrix will be given by the product of their eigenvalues. So here eigenvalue, we have lambda 1 equals to 4 and lambda 1 equals to 4 and lambda 2 equals to 5. Okay, so just multiply 4 and 5, that is 20. So 20 will be your answer, or 20 will be your det of the matrix. So again, this is a property of the eigenvalue and eigenvalue property. Okay, so 20 is the correct answer. This is an integer type question, I think, so that is why 20 is the correct answer. Okay, so is it clear? Okay. So again, for this week specially, you have to again go back to your properties of eigenvalue and eigenvector. Mainly you have to understand how to calculate eigenvector and eigenvalue, and second thing, again take a look at how to calculate the singular value decomposition and eigenvalue decomposition. That can also come here in the question. It has not asked, but again that can also be asked just to find eigenvalue decomposition. Question can come like what is the V inverse, like what is the inverse of that eigenvector matrix, and singular value decomposition can be like what is the U matrix or what is the VT transpose matrix. So that can be asked. Okay, so please go and take a look on that two question and how to find eigenvector, eigenvalue. Okay, so this is the main important thing that you need to focus for this week. Okay, and second thing is all the properties of the principal component. Why we are projecting principal component on the eigen vectors? What is the role of eigenvalue in the principal component analysis? All this thing. Okay, so this thing again take a look at it. Okay, so by this this is the end of the class. So any doubt, especially for today's lecture, any doubt?
Just one question. So
Yes.
we are trying to find the maximum value in these vectors. So what is the significance of that? There were some questions now where
Yeah.
it is asking what
E-
is the maximum value.
Eigenvalue, eigenvalue gives the variance of data in that particular eigenvector. Okay, so more will be the eigenvalue, the more variance that your principal component will cover, or your eigen vector will cover. So that is the concept.
Okay, okay. So that is the concept of PCA.
Yeah. Okay. So any particular doubt? And codes, I have given codes for everything. Also I have given a code for this singular value decomposition and eigen value decomposition for a phase data set. So again, you can open the code, copy to your drive, and you can just operate. Every concept I have given in the comments, so you can just operate on your own. Okay, just copy to your drive and
Okay.
run the code, and you can see the things. Okay.
And similar to that, in SVD also, do we find the maximum value or it is only the concept in PCA?
Yeah, SVD also maximum value, because SVD also we are finding the sigma matrix, right? Sigma matrix is nothing but a matrix consisting of singular values. Singular values is nothing but your square root of this eigen values. Okay.
Okay, got it.
Singular value decomposition we are doing for matrix, rectangular matrix. So this is the only difference. Or this eigen value.
Finally, we will be finding the value which will be capturing the maximum variance.
Yes, yes, yes.
Then we can plot it like which is capturing more value.
Yes, so these values will have more variance in the for that eigenvector. This value will give the more variance. So that is the
But the
concept.
steps will be common, like calculating covariance,
Yeah,
and
yeah, yeah, yeah.
that will be common, but the final step will be different.
Yes, yes, yes,
What? Thank you.
Sir,
yes. Please.
where is the application of PCA, sir? Where we can apply in a real time?
Real time. This is a dimensionality reduction, right?
Okay,
So in real data, like you have 10,000 features. So
okay.
to visualize your data first, PCA helps in visualizing your data. If you can, you have 1,000 features. So instead of 1,000 feature, if you can visualize in a different dimension, that are the eigenvector, and you can project your data, or you can project the maximum like 95% variance of data in 100 components. So that will be a dimensionality reduction, right? You are doing a dimensionality reduction by 100 times. You have 1,000 feature, and now you are projecting your data in 100 principal components, right? So that is a dimensionality reduction technique. So this you can apply in any field. Okay, to do the dimensionality
Uh,
reduction.
to reduce the dimension, we are using the PCA, sir.
Yes, yes, to reduce the dimension we are using the PCA. But see, the
Sir,
dimensionality reduction can be of many types. Okay, one is just you just which dimension you feel it is not important, you are just eliminating it. Okay, that you can do. That is called feature selection and feature elimination. So that is feature elimination. But in PCA we are not doing feature elimination completely. So that two things are different. In PCA what we are doing is we are projecting our data into a different axis, and see that in those axes in which direction we are covering the more variance, and then we are eliminating the other principal components. So these two things are a bit different. Okay, so you can just do the feature elimination, like whatever feature you feel not important, you can just eliminate it. That you can do, but that is not PCA. We are projecting into different basis. Okay, that basis are nothing but your eigenvector, and in that basis we are finding out that top k bases which are covering the maximum variance of the data, other we are eliminating. So by that we are doing the PCA. Okay,
Okay.
this is
sir,
the
in this
yeah.
PCA, you have shown only two dimensions. If you have 124, 156 features, how will you show it that way?
How
Or
will
you
you
have to?
show it? Means visualize it.
Acha.
Visualize it. You are asking about visualization.
Yes, sir.
Visualization you cannot visualize more than 3 dimension, right? 3D only maximum we can visualize. We
Yes, sir.
cannot visualize more than 3 dimension. Okay, but like I have shown in the code, you were there, right, when I was showing the code? We have
Yes, sir.
784 features, but with 154 principal component only, we are getting our reconstruction error very little, like 0.01, or we are covering more than 95% of variance with just 154 component. Okay, principal component.
Yes, sir.
So that is the thing.
Sir, from where I can download the code you have shared?
I have given you the link, right? This is the drive link. I have pinned it. This is the drive link. You open the drive, you go to a folder called DL codes. In that DL codes, you will see all the codes. You find out where is the PCA written, and you can just open the code, copy to your drive, and then run the code. Okay? Kindly
Sorry, sir.
copy. Yeah, please.
Where is the link?
I have just pinned it. Okay. Okay, let me share it
Where
again.
I can see the link, sir? Okay.
This is the link. Okay, this is the link to my folder. Let me show you again. Yeah, so
In coordinate.
yeah, so
Okay.
this is the folder. Okay, this is the folder. These are all the presentation. This is the week 5 presentation that I'm discussing with you. You go to the folder DL codes. Okay, just open the DL codes. These are all the codes. Like last week we have discussed like gradient descent, momentum based gradient descent, etc. Today this is the code 13. You open the 13. I will delete the 12. Okay, this is the 13 code. This you please do open. PC on MNIST dataset. 12 I will just delete. Okay, I will remove. 13 code you just open it, and this is the PCA that I have shown you. Again I am showing you. This is the code related to PCA. So I think it will take, yeah. So this is the code related to PCA that we have just discussed. As I am running in on my drive, so there is no option like copy to my drive, but whenever you will be opening the code, there will be an option here coming copy to drive. You just copy the drive to your code, and then you can run it. Okay, and also I have given you a code for this difference between value decomposition and singular value decomposition. Here, as we are doing operating on image dataset, so actually the m cross m vector will be same. Okay, so here we are not getting so much difference, but you can apply it to different m cross n matrix and m cross m matrix, and you can see the things. But here the code, this is the code, so code you can just see. Okay. So is this clear? Today's lecture, is it clear to all of you?
Yes.
Okay. So by this I am ending the session for today. We will meet on the next Tuesday. Okay.
Thank you, sir.
Okay. Bye.
Thank you.